Hello, hello. We are starting our last chapter. This is chapter 12. We're going to be jumping in with 12.1. Chapter 12 has a lot to do with circles. And you're going to see a lot of lines and angles that deal with circles. So central angles and arcs and things like that. So we're going to start with 12.1, which gets broken into two different sections. 12.1a is, they're both tangent lines that we're going to be dealing with. It's not SOHCAHTOA. It's not tangent like that. It is a particular type of line, and you can see it in this picture right here. When we say something is tangent to a circle, which is what you're seeing here, that is a line in the plane of a circle that intersects the circle at exactly one point. Okay, so we would say this red line is tangent because it hits the circle only at that one point. Doesn't cut through in two places, it's exactly one point, okay? The point we call a point of tangency, and that's just the point where it is tangent to the circle, okay? So that's a point of tangency. So there are a couple theorems here. Theorem 12.1 says if a line is tangent to a circle, then the line is perpendicular. Oh, ran out of room. Perpendicular to the radius at the point of tangency, sorry. At the point of tangency. So if you look at this picture, here is your tangent line, here is your radius. Notice those two form a 90-degree angle, and that will happen every single time. If a line is tangent, it will be perpendicular. Okay, and then the converse is also true, so I just wrote the converse out here. If a line in the plane of a circle is perpendicular to the radius at the endpoint on a circle, then that line must be tangent. So sometimes they'll say, hey, this line is tangent, therefore we know it's perpendicular. Other times they'll say, hey, these lines are perpendicular, therefore we know that the line is tangent. Okay? All right, so here's what we're going to be doing with this. This first example, thinking about what we know here, it says ML and MN are tangent. Okay, so this line and this line segment are tangent to the circle. What is the value of x? And notice we're talking degrees here, okay? If you look, we have, let's go back to red here. We have this figure that we're working with. That's a quadrilateral, okay? And we know in a quadrilateral, all of the angles will add up to 360 degrees. Well, we know this one's 117. We know this is x. And we do know something about the other two. Because they told us those lines are tangent, that means they're perpendicular to each radius. So that means this one is 90 and this one is 90. So you're going 117 plus 90 plus 90 plus x. So those four angles all together should add up to 360. So we're going to go 360 minus 117 minus 90 minus 90. And that leaves us with x being 63 degrees. Okay, so that one made a quadrilateral. Now look at example 2 here. It says ED is tangent. Okay, so this is tangent to the circle. And this is a diameter, which means you have a radius here. So we know that this is 90 degrees. It has to be perpendicular because it goes through the center. So to find the value of x, now this one is slightly different. What do you need to do with that? You would take 90, 38, and x, and here's the difference. It's a triangle now. So that means it has to add up to 180. So you're going to go 180 minus 90 minus 38 is 52. Okay, so x here would be 52 degrees. All right, moving right along. I got two more for you. Number 3 here, it says the CN Tower in Toronto, Canada, has an observation deck 447 meters above ground level. About how far is it from the observation deck to the horizon if Earth's radius is about 6,400 kilometers? So we laid this picture out for you already. What they did here was they converted 447 meters to about 0.45 kilometers. Okay, so they did that conversion for you. We won't make you do a conversion like that. But what they're asking is, how far is it from the observation deck, which is at T, to the horizon, which is right here. So we're looking for this length. And think about what we know. We know that it is tangent to the circle. You know what? I didn't say that right there, but that is tangent, okay? We will tell you that it's tangent. So what you're going to do is you're going to look at this and say, okay, well, I know if it's tangent and I have a radius that this is perpendicular, right? So really we're looking at a triangle where we know 2 of the 3 sides, so we can do Pythagorean theorem to solve it. So it's going to look like this. We're going to do 6,400 kilometers. You know what? Let's not label it right now. We'll label it at the end. So 6,400 squared, that is this EC side, plus, and then we'll do x squared, because that's the other leg of the right triangle, equals, and then the third leg is this whole side. And what you need to make sure of is we know this distance, because it's a radius, is 6,400 kilometers, but we need to add the 0.45 to that. So it would be equals 6,400.45 squared. Okay, so it's just Pythagorean theorem. If we plug this in, we're going to subtract 6,400 squared. Make sure you're plugging it in that way. So 6,400.45 squared minus 6,400 squared. You get x squared equals 5,760.2025. Okay. And then from there, we just square root. So you can just go second, the square root button, and then second, and then that little answer key, ANS, and that will take that last number and drop it in. And x comes out to 75.8959, and that number just keeps going. So about how far is it from the observation deck, we would say it's approximately 76 kilometers away. Okay. Okay, last one. And this one can be a little bit tricky. There's a little extra work involved here. What we're going to do, we're looking for the radius now. The nice thing is a radius wherever you put it. So if it's x here, then it's also x here, okay? And we do have a right triangle. So to solve this one, we're going to plug this into the Pythagorean theorem. So it'll be x squared plus 12 squared equals, and now here's where it's a little tricky. This is x plus 8 squared. Okay. Now, for some of you, if you know the triples well, and you see this and you go, oh, there's a 12. Okay, well, I know one of the Pythagorean triples is 5, 12, 13. Let's check it. If I plug in a 5 and I plug in a 5, I get 5, 12, 13. Oh, that works. So I know x is 5. I know that is not most of you or even very many of you, but some of you know your triples really well, and you can do that. If you know the triple and you see a number and you go, oh, I know that's 3, 4, 5, or I know it's 6, 8, 10, or I know it's 7, 24, 25. Okay, there's a lot of very common triples. That's fine. If you don't, what you need to do is this setup. And the place that people get a little confused here is with this. Be very careful. x plus 8 squared is not x squared plus 8 squared, right? Do you remember what x plus 8 squared is? It's x plus 8 times x plus 8, right? Which means we have to FOIL. So this is going to be x squared plus 8x plus 8x plus 64 equals x squared plus 144. Okay, so now when we solve it, look how nicely this works. Take away an x squared here, take away an x squared here, those are gone, and we have 144 equals 16x plus 64. Now we can take away the 64. So you get 144 minus 64 is 80. So we have 80 equals 16x. And then if we divide by 16, you should see 80 divided by 16, we already got our answer, is 5. Okay, so the length of our radius in this problem would be 5, which is what we found at the beginning, just using triples. So just be careful with that one. There's a little bit of extra work there, just remembering to FOIL. Okay, and that is it for 12.1a.